All right, try this again. Really sorry. Okay, so we'll give it a minute, let people jump over, and then we'll get started. Hello. So as we go through this, if there's any questions you guys have, obviously just shoot a comment on the side and then we'll take a look at it and we'll just do that. Again, sorry about the confusion beforehand. All right. So, all right. So here we go. So we'll start with the conceptual questions for review for test part 2. So part 1 is list the different types of charges. Really, we just know that things are positive, protons positive, electrons are negative, and neutrons would be neutral. We know for 2 what type of charges will attract or repel. We know opposites attract and same charges repel. In order to become charged, what must be transferred? Hi, Joy. Hello, Mike, by the way. So question 3, whenever we charge something, we always transfer electrons, only electrons. So remember, if you gain electrons, you become negatively charged, and if you lose electrons, you become positively charged. You cannot be charged by a transfer of protons. That doesn't happen. Question 4, conductor versus an insulator. All right, conductors allow for the transfer electrons to happen very easily, and insulators do not. So metals are conductors, right? Electricity can flow from one end to the other without really any resistance, which we'll talk about in the next chapter. Insulators, there's too much stuff in the way, the electrons can't move from one end to the other. 5, how does charging by friction take place? So if you charge by the way of friction, when 2 objects rub together, all right, one object is going to transfer its electrons to the other object. As that surface is gaining electrons, that item is becoming partially negative, and then it becomes negatively charged. So we didn't necessarily use the terms for question 6, thief versus victim, but give an example of charging by friction to distinguish what the thief is and what the victim is. So if we took those pipes, the PVC pipes from the static lab, when we rub the rabbit fur on them, all right, the rabbit fur is giving electrons to the PVC pipe, so the PVC pipe is becoming charged. So in that case, the thief is the PVC pipe, and the victim would be the rabbit's fur, because the victim is losing the electrons and the thief is taking them. 7, how does charging by conduction work? It's basically what we just talked about. When one item that is charged touches another item, the electrons are going to move from the first item to the second item. And yes, Christine, we're going to take the test through Google Classroom. I'm going to make a form for you guys and all that stuff. I was going to tell you about the format for the test after the review was over. Just FYI, I won't forget about that. So that's so you have a charged item. It touches an item that is not charged, right? That difference in charge, the electrons will transfer over to the other item, and that is charging by conduction. 8, charging by conduction. When do you guys charge the PVC pipes, right? We just kind of talked about it before. So, right, as the pipe is rubbing, the fur is slid across the PVC pipe. All right, the electrons transfer. All right, charges one item to the other. Oh no, I apologize, not a good example. Charging by conduction. charging by conduction. When we take our feet and we rub them against the floor, that's charging by friction. And then we become statically charged. And then we touch somebody else, that is charging by conduction. We are charged, we are touching somebody who is neutral, all right? And that causes the electrons to transfer from the charged item to the non-charged item. That is charging by conduction. If you're grounded, it means you are touching the earth. And we know the earth is where all electrons will flow to. So when you're grounded, it's basically conductive charging into the earth. All right. Charging by induction. So when you induce a charge, you're actually not necessarily making an object charged, as opposed to just making the object feel as if it's charged. All right. So if we bring a negatively charged item towards something that is neutral, right? The electrons in the neutral item will basically try to get as far away as possible from the negatively charged item. That means the side closest to the negatively charged item becomes positively charged, while the other side becomes negatively charged. And right to lead us into 11, when you guys charged the PVC rod and then you brought it near pieces of paper, the paper was attracted right up to the pipe. That's charging via induction, right? You didn't touch the other object or the paper, and yet you were still able to basically produce a charge inside of it and then cause this attractive force to pull the paper up to the PVC pipe. Right. So that's the 11 questions as far as the conceptual questions go from this. Does anybody have any questions not related to the math questions in the review? If you do, feel free, hit me up through this chat. I'll wait like a minute or so. Also, while we're waiting, sure thing, Joy. I posted the answer keys to the review, the math questions in the classroom. So we'll go over them as well. And if you want to see the actual work done, I have it posted right to the classroom. All right. Okay. So something is charged positively or negatively. Let's just say it's negatively charged, and it touches something else that is neutral. All right. The difference in one item being negative and one item being positive, that's going to cause the electrons to flow from basically the more negative item to the neutral item. And because you are making contact to produce that flow of electrons, that's charging by conduction. So if you are statically charged because you rubbed your feet across the ground with your socks on, and then you touch somebody else, because there's a difference in charge between you and the person you touched, that's going to cause electrons to flow from the negative item to the neutral item, and then that is going to cause conduction or conductive charge. That's 8. Does that work for 8? Six. All right, good. All right, for 6, give an example of charging by friction to distinguish what the victim and thief is. Okay. So if you are rubbing your socks across the floor, we know that basically the earth is grounded, so it's going to basically take any electrons from you. So as you rub your feet across the floor, right, here's the floor, you're rubbing your feet across from there, right, you are basically giving the earth your electrons. So you could say that in that case, the thief who's stealing your electrons is the earth, and then who's the victim? Well, your feet are the victim. You are losing electrons, and that is charging by friction. So it's just when two objects rub together, and then whoever is taking the electrons, that would be considered the thief, and whoever is losing the electrons, you could say is the victim. Don't really worry too much about the terms thief and victim. Just know that one item is going to be donating or giving its electrons away, whether it wants to or not, and the other one is going to be gaining the electrons. Right? Does that work for 6? No problem, Ellie. Definitely can do that. I think it's also going to save to my YouTube channel as well. Sure. Nasir, I'll draw 11 out. I think it makes it a little easier to draw 11 out. So give me a second. Okay. So let's say you have this at first. So you have some item that's negative and it's brought towards some item that is neutral. Okay, so that's how it starts. Well, the item is going to stay negative, and we know opposites attract and like charges repel. So when we bring it closer, this is what happens. Okay? All of the positive charges basically kind of stay put, but the negative charges get as far away as possible because we know same charges repel and opposites attract. And now that there is this positive end and a negative end, that's going to cause an attraction from one end to the other. Right, and that's so imagine the paper. We know the paper was neutral, so it's like this in that lab, and the rod was charged. Okay, and all of a sudden the paper jumped up to the rod. Well, that's because the positive charge ends and the negative end from the rod, or vice versa. This could have been positive and that could have been negative. That part doesn't really matter. But the opposite effect here causes the two things to come together, and that's charging via induction. Does that work for 11? All right. Okay. So any other questions before the math? Okay. All right. Thank you. Thank you. All right. So question 1. All right. So first off, please remember, all right, when we look at question 1, it says Q2 and Q3 are held fixed. All right. Find the net force. Remember, when you're finding the net electric force, you want to use the formula that's F equals K times Q1 Q2 over R squared. All right. Forces between two different charges. All right. Please remember to use the right equation. If you use the wrong equation on that tomorrow, it's going to cost you a lot of points because I can't distinguish if you know what you're doing or if you just made a simple mistake. All right. So anyway, so we use that equation for both things. And if you have the work in front of you, it says review part 2 and question 1. So I found F12 and then I found F13 respectively. All right, and now I'm going to look. Okay, so if you have this in front of you, we know that all 3 charges are negative because Q2 and Q3 are listed as negative and Q1 is an electron. So we know same charges repel each other. So if we look between just Q1 and Q2, just between the two of them, Q1 is going to basically be pushed to the right because they repel each other. So Q2 is going to want to travel to the left. Q1 is going to want to go to the right. We don't care about Q2, just Q1. So Q1 is going to the right. Between Q1 and Q3, they're both negative. They're going to repel. Q3 is going to kind of push Q1 to the left. All right, so Q2 is pushing Q1 to the right. Q3 is pushing Q1 to the left. So because they're opposites, when we find the net force, we have to subtract the two numbers, right? I, again, recommend writing it out, as silly as it sounds. That's what I have at the bottom of the paper. It says 9.22 E negative 14 minus 9.26 E negative 14 equals, and I got 4.76 E to the negative 16th newtons, right? And then my answer was also to the right. And I figured that out because my answer is negative. I didn't write it negative actually on the worksheet. That's a mistake. That's my bad. So if I look at it, since the direction I made negative was the force between 1 and 3, and my answer is negative, that's I know it's going to the right. So that's question 1. Any questions about question 1. Okay. All right. Question 2. Oh. He said the math review questions. Yes, they should be on there. I'm pretty sure they're posted on there. Boy. Make sure. So, yeah, here's the answer keys to the math questions from Friday's review. So that's what they're at. They're on there. Okay. Nasir, did you have a question? Or are you good? No, that's the same thing, right? Because technically, subtraction is just adding something that's positive and something that's negative. So you could look at it either way. It doesn't matter. The key thing to remember is, and I didn't say this, doesn't matter what this problem technically. Remember, when you solve for electric force or electric field, always start with it being positive and then use the direction between all of the forces or fields to determine what's positive and what's going to be negative. So just watch that one thing. But no, that's the same thing. Does that answer your question? No problem. Okay. 2. So find the net electric field. So unlike 1, where we found force, 2, we're finding electric field. So that's E equals K. Yeah, that's yes, Kevin. I forgot to make my answer negative. I was just looking at the numbers. So it is to the right, like I have written down, but my answer in the review should not be positive 4.7 times 10 to the negative 16th. It should be negative 4.7. That's my bad. Did I clear that up, Kevin? Cool, thank you. All right, 2. So electric field, right? E equals K times Q times R squared. Remember, when we find fields, we are finding them at some point in space where there is no other charge. So it's one charge and that's it. All right, so I know there's a F in field, but don't use the force equation that starts with an F. Net electric fields, E equals K Q divided by R squared. Excuse me. So for number 2, find both electric fields just using that formula. Remember, it's from point 1. So the distance for that first charge is 4, because from -3 to 1 is 4. And then the radius for the 8.7 charge is 8. So you solve for both. Okay? And I have my values listed on the review. All right, again, make sure everything starts off as positive. Afterwards, all right, you have to ask yourself, which way are fields pointing with respect to this specific point in space that we're looking at? So in question 2, the magic space is the number 1. So when we look at the positive 5.4 charge, we know electric field lines always exit positive charges. So those lines are going to point from the 5.4 towards the 1, so to the right. So that's why under my thing that says E -3, it's 3037.5 to the right. Okay. Then I look at the 8.7 charge. That's negative. Field lines always enter negative charges. So this line is going to point from the 1 towards -9, or sorry, towards the 9, right? Because it's going to enter that 9 charge, the charge at 9, because it's negative. So because it's doing that, that's also pointing to the right. So that's why both arrows point to the right. And then since they go in the same direction, you add the 2 together. And that's how I got the answer 4206.9 newtons per coulomb, and then to the right. Does anybody have any questions about number 2? Give another like 10 seconds or so. All right. So here we go. Question 3. Now we're doing this in 2 dimensions. All right. So it's the same process for A and B, just like we did before. The only difference is we have 2D. So the only part that kind of gets funny is when we talk about direction of both. So let's look at 3A. All right, so in 3A, we find the field between charge 1 and 2, or the force between 1 and 2 for letter A. That's 76.86. And we find the force between Q2 and Q3. That's 117.18. All right, starts with that. All right, and then we look, because Q2 is the star charge. So in the beginning, Q1 and Q2 are opposites, so they're going to attract. That means Q2 is going to be pulled up by Q1, so that's why the arrow next to F12 is up. And then Q2 and Q3 are opposites. Q2 is going to go to the right. That's why the arrow next to F23 points to the right. All right. So now we have our two-dimensional problem. We basically have 2 vectors. So we build an XY chart. All right, and then we look at F12. Since it's pointing straight up, there is no X component, it's all in the Y. Between F23, there is no Y component, it's all in the X. And then for the direction, F12 points up, that's a positive direction in the Y, and F23 points to the right, and that is a positive direction to the right. So that's why everything stays positive, and then it's the Pythagorean theorem, and then inverse tan of Y over X. And this is in quadrant 1, so the angle stays the same. All right, so I got 140 newtons for the net electric force, and the angle was 33.2 degrees. All right, any questions about 3A? All right. For 3B, it's the exact same problem. All right, so I'm not going to go through it as in depth. The answers are on the paper. And then you just basically have to look at this one because it's talking about Q2 being empty and the net electric field. We know fields enter negative charges. So the net field on Q1 from where Q2 is, those charges are going to be pointing up. So that's why the E1 field is positive in the Y. And then same thing, Q3 is negative, those field lines are going to enter. So those field lines are pointing to the right. So that's why, again, just like in the first question, everything is positive. We plug it into our XY chart, and then we get our value for the resultant net electric field and theta. All right. So any questions about A or B? All right. All right, so on to C and D. Okay, for question C, we're trying to find the net electric force at Q1. All right, so guys, the problem is the same as before. Yes. Not even necessarily the test charge. That's just like the spot in space. But yeah, basically, how is the test charge going to react to Q1 and to Q3? And since the test charge is positive, right? That test charge would be pulled up by Q1 and it would be pulled to the right by Q3. You could definitely think of it that way too. If you do it that way, your directions will always be right. It'll work that way. Just remember that test charges are always positive. Okay. For C, so we look at this. We find the forces just like we did before. So find the force between 1 and 2 and 1 and 3. Don't worry about the fact that it's a triangle or anything like that right now. So you find the two forces. The force between 1 and 2, okay, is going to pull Q1 down because they're opposites. So that's why the force between 1 and 2 is pointing down on the Y. Right. The force between Q1 and Q3, they are the same charge. So they are going to repulse each other. So that's why my arrow points up and to the left for the force between 1 and 3. Right. So I can take my values, I couldn't put them into my ABR chart. For force 1, 2, it's 0, and then the full value in the Y, but negative because it's pointing down. For F1, 3, because my arrow is in 2D, I must find its X and Y components using sine and cosine for the Y and X axis respectively. So to find out the X component for F1, 3, it's the force, which is 51.1, cosine 45, and then repeat with sine 45, right? And that'll get you 36.1 for both numbers. Again, everything stays positive to start. Then you look at your arrow that we drew. The arrow we drew for F13 is up and to the left. So we know if you're going to the left in the x-axis, you are negative. So that's why the 36.1 in the x is negative. But we know in the y, if you are going up, you are positive. So that's why the 36.1 remains positive in the y. All right. And then we go through everything we've done before. Solve for r, do the Pythagorean theorem. Make sure you plug in positive values, okay? And then find theta. When I find theta, I get 48 degrees, but I have to look back at my two R values. They are both negative, okay? So if you go to the left and you go down on the quadrant grid, you are in quadrant 3. So you have to add 180 to your answer. So 48 plus 180 becomes 228 degrees. All right, that is C. All right, so that's the only thing different between A and C is make sure you just have to worry about if your direction is in 2D, before you can plug it into your XY chart, you just have to use cosine for X and sine for Y. And I don't remember if it's Maddie or Jill, but one of you just make sure you have the right calculator out. All right, any questions about 3C? Yep, see? The things I miss. Yes, I was about to say inertia, Mike. I kid you not. It's about to pop out of my head. Good times. All right, let's look at D. Yeah, I miss all you guys too. I miss you guys too. Hopefully we'll see each other soon enough. All right. Me too. Okay. All right, so let's do D. So again, Q1 is our test charge. It's like not really there for this problem. So if we look at Q2, when we solve for the electric field at 2, it's going to be pulled up. So that's why the arrow in E2 points up. And then if we look at E3, all right, since Q3 is negative, that's actually going to pull that charge at Q1. Remember, Q1's not really there. So that that spot, those field lines are going to be entering Q3. So they're actually going down and to the right. So again, we build our XY grid just like we've done before. For E1, there's no X value and the Y value is all of it, and it's positive because it's Q2 is having the field lines point up and away from Q2. And then for E3, because our arrow is in 2 dimensions, we have to again use sine and cosine, and we do. And that's how we get our numbers for E3. And then since we look at our arrow, it's going down and to the right. Because it's going to the right, that means the X value is positive, but it is going down, so the Y value is negative. And then from there, we just do, we solve for R, we do the Pythagorean theorem, and we find the inverse tan, we find theta, and theta is 48 degrees, but we both look at both of our R's, they are both positive, so we are in quadrant 1, so we don't have to actually do anything to the angle, so that's why it stays the same. And that is the review as far as what I gave you guys on Friday. So any questions about that or anything else regarded to this? And then I'll tell you about the format real quick, and then, yeah, get on with your day. So I think I'm trying it tomorrow with my my AP class. We're trying to do Zoom tomorrow. So if I want to see how it goes, but I would definitely love to do a Zoom session. The only thing I don't know about Zoom is that if we do something like that, I don't know if it records it for anybody that can't be there live. I think YouTube Live will record this. So people who couldn't see it right now are able to see it. I don't know if Zoom does that. So I don't want to necessarily punish people if they can't do it, but we could still do a Zoom at some point. Definitely. It'd be fun to hear each other and see each other as well. Test's going to be timed. No, no. I mean, I guess what we'll do is this. You have to get it done by tomorrow, and it should take you, I would say, an hour. So I guess when, no, don't worry about the timing part. It's too hard right now. So no, it'll shoot up online between 8 and 8:30 tomorrow morning, and it just has to get done by 11:59 p.m. tomorrow night. Just make it easy. It'll be all right. So that's that. Any questions real quick about the review or anything else? And I'll tell you about the test. All right. So basically, it's going to be multiple choice via Google Forms, all right, and then some open-ended questions. It's all going to be Google Forms, all right, via Google Forms. And then for the math questions, right, you're going to have to send me examples of your work. So you're going to have to take a picture of your work on paper and then just send it to me either through Reminds, okay, which is no big deal, or if you want to, if you can somehow, excuse me, if your camera's open on your laptop, if you guys have taken off all the fun tape and Faust stickers that you guys put over it, if you want to take a picture with your webcam and then you can share with me via Google, just that somehow you just need to make sure that I see an example of your work. Okay, and that also in case you guys make any mistakes and the answers aren't there that you're getting are wrong. If you have your work, I can get you lots of what's it called? I'm sorry. I get you your partial credit. All right. I don't know, and I got to actually write it because I'm going to have to try to figure out how to do stuff with Google. I can tell you this. You won't have to draw any electric fields on the test. All the electric field questions all have drawn for you, and then I'll be asking you questions about it. So I might draw, 2 electric fields, and I won't label them anything as positive or negative, and then you'll have to answer like questions like, can you tell which one's positive, which one's negative, or which one has the greater field? But instead of you guys doing any of the drawing, I'll do the pictures, and then you guys would answer the questions there. And the equation will be posted on the test, and yeah. you know, guys, this test is not going to be monitored. I can't monitor this test, so yes. Does anybody have any other questions? All right. Well, guys, it was awesome seeing you virtually on the side. Um, Good luck next week. Hopefully, we'll be back sooner rather than later. And be good. And if you guys have any questions, don't hesitate to let me know. And I hope to see you guys all again soon. Thank you, Mike. You do the same. Stay safe, everyone. Be smart. Don't hoard all the toilet paper. It'll all be okay. We'll be back at WHS soon enough. Of course, of course. I miss you guys all. This is good for me too. I enjoy it a lot. It's like the end of the day. Bye. Thank you. Thank you, Joy. You too. All right, guys. Have a good one.